In this screencast, we're just going to look at where vector spaces come from. The idea is when we're dealing with vectors in Rn, it satisfies a bunch of properties. The sum of two vectors is another vector. The product of a real number and a vector v is another vector, called the scalar multiple of a vector. And these two operations, vector addition and scalar multiplication, satisfy the following 8 axioms. The idea is that it doesn't matter where you put parentheses when you add vectors. It doesn't matter what order you add them, and you can flop the order. There's a 0 vector, and if you add the 0 vector to another vector, you get out the vector you started with. Every vector has an additive inverse. In other words, you can turn every vector around so that you can add them together to get the 0 vector. In addition, scalar multiplication distributes across vector addition. In other words, you can distribute either across the addition in scalar multiplication or the addition in the real numbers. These two are different because here you're adding vectors, here you're adding numbers, and it doesn't matter which way you do things. You can either do the addition before or after, before or after. In addition, you can multiply before, you can multiply by a scalar before, or you can before you multiply by a vector, or you can multiply by a scalar and then a scalar, or if you multiply by 1, it does nothing to the vector. These 8 properties, together with the top 2, form what are called the 10 properties that we're going to use to generalize to a vector space. Before we get to a vector space, we're just going to look and notice that this exact same set of properties follows through if you replace every vector in Rn with a matrix. So if you just consider m by n matrices, so a 5 by 10 matrix, the sum of two 5 by 10 matrices is another 5 by 10 matrix. And you can multiply every single number inside the matrix by the same real number and get another matrix out. And these two operations, the matrix sum and the scalar multiple of a matrix, again satisfies the exact same set of properties. This is just a copy of what happened before, where I replaced the word vector with the word matrix. So what we're going to do is we're going to remove Rn, we're going to remove m sub mn. This notation right here is the notation used to talk about the set of all m by n matrices. And instead we're just going to say a vector space is a set of objects that satisfy, well, you need to have a way of adding things and you need a way of having multiplying things. So that's what our definition of a vector space is. It's just an abstraction of what we do with vectors and matrices. A real vector space, we use the word real because you could use complex numbers instead of real numbers as your scalars. It's a set together with two operations. You need a way of adding and you need a way of multiplying vectors. These are beginning with a C because they're called the closure axioms. It means that if you take any two vectors and add them together, you get a vector in the set. If you take a scalar and multiply it by a vector, you get something that's in the set. And again, it needs to satisfy the exact same properties that were satisfied by the real numbers. Anything that satisfies that is a vector space. This is a very abstract idea, and we're going to be working throughout the semester at coming to grips with it. But right now, really, it's just take the set of vectors in Rn, and what other kinds of sets can you work with in the exact same way that you worked with the set of vectors in Rn. That completes the screen.